Hello, good evening, good afternoon, good day, good morning, wherever you are in the world. Let's transition in first. There we go. And welcome again to another stream for Freaky Physics. We have a live lesson today. We have CJ today again. We have the same topic from before, which is about global warming. All right, and here he is. So I'll just join the lesson now. Hi, CJ. Oh, hold on. My camera's still off.
Hello.
Hi. Okay, can you hear me? Great.
Yes.
Okay, good. So, yeah, sorry about the confusion last Tuesday. I was actually surprised myself it was there. Yeah. Uh all right. Anyway, where were we? We were
8.2.
8.2. I think we kind of finished two parts of it. The absorption of light, which is the absorption of light, which involves albedo and black body radiation, and then the
Mm-hmm.
emission of the infrared radiation, right? Okay.
Yeah.
Um okay, let me just get to the board now. Oh, it's still not up. Hold on.
Wait, I'm pasting this question
Mm-hmm.
because yeah, I pasted in the chat.
Okay, hold on. Let me put that up as well. All right, let's see the chat real quick. Okay. Okay, it's still loading here. The moon. Okay, there we go. Albedo. What must its average temperature be in Kelvin? All right, so this is what actually I wanted to kind of go to this particular problem. Okay, so we'll get to this in a while. I'll just copy the text. Copy that and I'll paste that here on the board. Okay. All right, so in order for us to answer
Mm-hmm.
this, we're going to have to review the thing we were doing last time, right? Before that, I want to show you something. Okay. This particular thing here, you can imagine this is the reason why we have to take 1/4 of the area of the sphere when we're doing the intensity of radiation coming in, right? So if you think of this, I'll just say that this has a certain intensity I, right? So these is the sun. These are the sun's rays. Okay. Now you can see here that on this region, the intensity, all of these at this region, same intensity, right? And that's represented by equal widths. Okay, widths. Okay. Now, when the sunlight gets to the Earth's surface, at this particular point, it's still more or less the same intensity, right? So if the intensity here was I, the sunlight reaches this portion of the Earth with an intensity I, right? But if you look here at these regions, that intensity gets kind of spread out, or all that light gets spread out. Where does it get
Mm-hmm.
spread out? It gets spread out on that area of the Earth. So the intensity here, let's just say I0 here to make it easier. So this is more or less I0 approximately. But here I is definitely gonna be much less than I0. Simply because all that energy from this region or from this section is spread out over here. Okay. The overall effect. So, all right. So what happens here before we continue? This side is dark, right? So this is dark. So the dark part, in essence, changes the area of the sphere. So from a total area A to just half of it, right? So that dark section. And then this little bit here, this spreading out here. So the spreading out, what it does is it takes it from half of A to half of that again, or A over 4. That's why we only use 1/4 of the area of the sphere, whether it's the Earth, the Moon, or whatever, when it's absorbing radiation. Okay, so this is more or less the reason. I was trying to explain this in a more visual manner, and I think this is the best one I can come up with at the moment. All right. Okay, so let's go now to your question here, which is about the moon receives the same intensity of solar radiation as the Earth. Now, before we go there, there's a value. Let me just get there. There's a value in the data booklet. It's called the solar constant. There. Let me just open that up so I can more or less get to that. Okay. So this value, which is called the solar constant, I'll copy that particular value here in the chat box, or not in the chat box, here on the board, but you will see this in the data booklet on this page. Okay, so let's go back here. Okay. All right, so we have all these fundamental constants here, and we're going to focus our attention on the solar constant S. Okay. Where is it in the data booklet? It's going to be somewhere here. So the solar constant is here at the bottom. Okay. So this value, the solar constant, is the intensity, the average intensity, solar constant. This is the average intensity of sunlight how to say it in a more technical way, at the top of the Earth's atmosphere. Okay. So again, so basically for you to solve this question, you will need this solar constant right there. Okay. Okay, so why do we have to say that statement there on top of the Earth's atmosphere? Because of the fact that albedo exists. The atmosphere will reflect some of the light. Clouds will reflect some of the light, and whatever else. Okay, so we have to take it here. So if we take a look here, let's just set it up first before we do the problem. This is the sun. Okay, and this is the Earth Moon system. And let's put the moon here. Okay. Since they are more or less on the same region, this means that the solar constant here on Earth is the same as the solar constant here. Okay. So in other words, you're going to have to use this value to solve for that. Now, anyway, it's given right here. This is also the solar constant. All right. Okay. So now we know that distance is the same. We know that this distance is 1.5 times 10 to the 8 kilometers. So that's going to be the same as 1.5 times 10 to the 11 meters. Right? Okay. So now we know the albedo of this moon. It's 0.120. What's the average temperature in Kelvin? Okay. So the idea here is you're going to have to start with this idea. Power in should be equal to power out for a body of constant temperature. Uniform or constant temperature. I'll use the word uniform. Okay. Okay. Before we complete this, what does it mean if the power in, the input power or the incoming power, is larger than the output power? This means the body will warm up, right? So warm up. Okay. And then similarly, when we have the other case wherein the power in is less than the power coming out of the system or out of the planet, Okay, the body or the planet, or in this case the moon, should cool down. So this is what we call the energy balance. So in energy balance, okay? Okay. So in this case, let's take a look at the formula sheet again. If we go back here, sorry, not that value. We'll use the formula in the data booklet. By the way, how do I sound? Because I'm trying a different position for the microphone right now. Do I sound the
It
same?
sounds the same to me.
Sounds the same.
Yeah.
All right. So, okay, there we go. Okay, so if we look here in the relevant section of the data booklet, which one is going to be useful? It's going to be this. It's going to be useful. Okay. And then, the solar power, the solar constant is also going to be useful. Okay. But here's the thing. This solar constant, if we go back here, this solar constant is basically an intensity. Right? And we know that intensity is defined as power over area. I'm going to write that as... So the incident power of light, to be specific, divided by the area wherein it's incident on. Okay? It's actually also mentioned right here. Like that, right? So, in other words, if I divide... Because this is the moon. The power into the moon is going to be some value. And the power out of the moon is going to be some value. But I'm going to divide this by... okay. This is going to be... I'm going to divide this first, the power output, by the area of the moon. Right? What do I divide with the power in? I'm going to have to divide this by 1/4 of that. So that's 1/4. I'm sorry. I'm going to have to divide this by the area of the moon as well. But just 1/4 of it. Because of, again, of our argument here. Okay? Alright. So because of this happens, we're going to get 1/4 of the intensity in should be equal to the intensity out. Okay? All right. Now we're going to put our value in. This has a value already. This intensity in is the solar constant. The 1.4 times 10 to the 3. This is 1.4 times 10 to the 3. Then you divide this by 4. That should be equal to the intensity out. Now, here, this is the idea here. We're going to say that this is now, let me just zoom that, let me just rewrite that real quick. So here, this actually is saying, I'll make that a bit bigger, power equals E sigma A T to the 4. This is the emissivity. We've discussed it before. This is the Stefan-Boltzmann constant. It's in the data booklet. This is the area of the body, and this is the temperature of the body in kelvins. Okay, so what we'll do now is if I divide both of these by A, this A cancels out, this A goes here, that's the intensity, right? So basically we're going to write here E sigma T to the 4. Okay, and now we're going to solve for the temperature. So let's just put that here now, 1.4 times 10 to the 3 over 4. Yeah, 4 is equal to emissivity. We're gonna treat this as a black body, right? Oh, we forgot something, but we'll get back to that. Okay, the emissivity is gonna be 1. Sigma has a value, and this one's an easy value to remember, but you can always check the data booklet to be sure. Okay, in my case, I've memorized this because it's quite easy to memorize. This is sigma, okay? This is E. And then the T to the 4, we don't know. I just want to point this out before we continue. Sigma, the Stefan-Boltzmann constant, is 5.67 times 10 to the 8. 5, 6, 7, 8.
That's called the sigma notation, or is
No, this is the
Why is it
Stefan
sigma?
Boltzmann constant.
Yeah, why is it called sigma?
Uh, that's the Greek letter sigma.
That's weird. I thought it was standard deviation.
Oh, in math, it means standard deviation in math. Okay.
Okay.
Okay. So, all right, carrying on, we forgot something. We forgot to take into account the albedo of the moon, right? So we're going to have to multiply the power in by the remnant. So in other words, we're going to have to multiply this by um 0.88. Where do we get that 0.88?
The albedo.
Yes, the albedo is 0.12, right?
Mm-hmm.
Okay. Sorry, let's put that in. So 0.88 times 1/4. Okay. So that gives us 0.22 at the end, right?
Mm-hmm.
Times. Okay. So we're going to have times 0.88 here. Times that over 4 is equal to the whole thing. And now we just calculate the temperature. That's going to be the fourth root of um 0.88 times 1.4 times 10 cubed all over 4 times 5.67 times 10 to the minus 8. Okay, we put that in the calculator and then we find the answer. Okay, so let's put that in. Let's see what we get. 0.88 times 1.4 exponent 3. Then divide that by 4 times 5.67 exponent negative 8. Okay, and that's the answer. And we take a fourth root, you just square it twice. So square root, then square root. So in this case, we get our temperature is equal to 271.48 Kelvin.
Mm.
Okay, now let's go back to the problem. It says that the moon should, it doesn't actually say that. What's the average temperature of the moon? It's this, which if we convert to degrees Celsius would be, we add 273, right? 273, or not add, but subtract. So minus 273, that's gonna be negative 1.5 degrees Celsius. 51, 52. Okay, which
Wait, 1.4 times 10 to the what?
negative, this one is 10 to the 3.
Then I got 73702. Oh, squared. Oh, fourth root. Oh,
Okay,
sorry.
fourth root. So you have to do a double square root. Okay, just be careful with that. Okay, so anyway, what does this mean? This means that the moon's average temperature is this. It doesn't mean it's always a temperature. There's gonna be spots wherein it's hotter and spots wherein it's colder. Okay, but there. Okay, so question. I'm gonna look for the value of the albedo of the Earth. Can you do a similar? Can you do the similar question? So I'll just change it to the Earth instead of the moon.
Wait. Um,
0.3. Okay. Okay, you have questions first, I guess, before we continue?
I just want to put it into my calculator.
Okay.
Oh, okay.
Got it all?
Yep.
Okay. Um okay, so I want you to redo this problem. I'll just put this onto a new board here. But I'm going to change it from the moon to the Earth. Okay. So now change it to Earth. Okay. So we'll just remove this and is at the distance. Given that the Earth okay, has an albedo of 0.3. What must the average temperature be in Kelvin? So again, it's the exact same process. You just make sure your numbers are correct.
Hmm.
You,
So square root for 0.7 times
mm-hmm.
1.4 times 10 to the 3
Uh-huh.
divided by
Divided by
4.
4, right? Equals
Stefan Boltzmann.
Stefan Boltzmann. Uh-huh. So I'll just put the value in. That's 5. Again, a really easy, a real fun number to memorize. Stefan
Mhm.
Boltzmann. And then
256. Wow, that's a cold Earth.
yeah, that's the temperature to the 4. And then if you calculate that, I'll just go straight to the point. You got 256 Kelvin, right?
Mm-hmm.
How many degrees Celsius is that to be sure?
Oh,
Yeah,
wait.
just to put
The
it into
formula.
perspective.
It is. Wait, I need to find it.
Well, think about it this way while you're finding it. It should be colder than
Yes.
the moon, right? Because it reflects more light. So it should be colder. All right. So again, it should be colder because it reflects more light.
Mm-hmm.
So let's take a look. This is how many?
Sorry.
How many degrees Celsius is that? That's negative 17
Negative
degrees.
15. Oh, 17?
Is it? Oh, hold on. Did I do it right?
Wait, I put the number wrong.
Okay.
Yeah, negative 17.
Negative 17 degrees, right? So in other words, yeah, that makes sense because since the Earth reflects more light, it should be colder than the moon. But it's
Mhm.
not, right?
Yeah.
So this is where we stopped last time, and this is where we will now continue with the whole concept. Okay, so quick recap again. If this were the Earth, we have energy in, we have energy out, and then we have energy going back, right?
Mm-hmm.
This is what we haven't done yet. We haven't done the energy going back to the Earth. So the Earth is radiating heat, but in the process, the atmosphere kind of prevents it from escaping. Okay, so that again, as we mentioned last time, the key idea here, E reflected or back. The key aspect here is the greenhouse effect, right? Okay, I just have a question before we continue. What do you know about the greenhouse effect? So I know where to start with this. Anything you know about it?
Um, is this something about like as like there's more pollution, like it's harder for the reflect energy to reflect out of our atmosphere?
Somewhat like that. Yes. So I'll just add. That's actually like I'm gonna.
Like as there's more carbon dioxide in our
Mm-hmm.
atmosphere, it's harder for the. Okay, I'll give an example of volcanoes. So volcanoes, they have like dust clouds.
Okay.
So while it's hard to have radiation come through, it's
Mm-hmm.
also hard for radiation to go out.
Right. Okay. So what you're saying is correct. Yeah. So in this case, the CO2, you said CO2, right? Um,
Yeah.
dumped by humans in the atmosphere. So I'm just gonna rephrase what you said. Tell me if I'm right, okay, or wrong. Dumped by humans, um, traps heat that would otherwise just traps heat. near the Earth, right?
Mhm.
Is this correct? More or less. Okay. Now the key fact here is this is the enhanced greenhouse effect. Okay. The greenhouse effect is essentially just this, but without this part. So the greenhouse effect is CO2. I'll add other things, CO2 and other greenhouse gases. I'll just label that as I'll just write that as full first greenhouse gases. Okay. Okay, CO2 and other greenhouse gases trap some heat near the surface of the earth. Okay. Now okay. And remember the greenhouse effect by itself is not bad. In fact, it's essential for life on earth. It's the enhanced greenhouse effect that's causing problems. Okay, so the enhanced one, I'll just write another word, additional. Okay. Okay. So how does this work? Right. Now the greenhouse effect works because of two things. Okay. The first thing is I'm gonna just put some, and I'm gonna literally just draw this like this. So in this case, this is the infrared or whatever other form of radiation from the sun. So it comes in like that.
Mhm.
Okay. So the sun, and we're focusing on the infrared. Okay. Now, I'm going to draw this in a slightly different way here. Tell me, what do you see the differences?
Oh, it's like ref I want to say like refracted. No,
No,
it's
it's not
reflected, but the wavelength changes.
correct. Well, half correct. It's not actually reflected, but the wavelength does change. So let's focus on that part first. So there's a
Oh, it's not
wavelength
reflected,
change.
it's absorbed and then emitted.
Yes, that's actually the uh process.
Yeah.
Okay? Okay. So
Oh,
in
a
this
wavelength increase, right?
mm-hmm. So the idea here, let's just put this in. Oh, by the way, before we do that, uh, so here uh, short wavelength infrared comes from the sun, right?
Mm-hmm.
And passes through the atmosphere and is absorbed by the earth. Absorbed by the ground. I'll just say by the ground, right? By the ground. Okay, excuse me. I'm getting hiccups. Okay, so anyway, that's what's happening on this side. Now later on when uh the ground is actually at the same time it is emitting, so the ground emits infrared radiation of longer wavelengths. Okay. The wavelength that it emits, this goes into one of the formulas that you've learned in astrophysics, and it's also mentioned here. This is all about the peak radiation, but I guess we'll go there later just to be sure that we're doing it right. But for now, let's do this part first. Okay. Now the thing here is, and here's the important part, I'm gonna draw part of the atmosphere like this. Okay. This is part of the atmosphere, and I'll just say that this is the greenhouse gases. These are the greenhouse gases. Let's use green for that. Okay. The greenhouse gases do this. Okay. What's happening here? There.
Mm. Oh, it's the greenhouse gas re- makes like traps the heat being emitted
Mm-hmm.
and makes it reflect back onto the surface.
Kind of like that. Okay, I'll fix that statement a little bit, but the idea is
Not
correct.
reflects, but like trapped.
Yeah. So
So it's forced to the back.
the idea here is the main idea here is the greenhouse gases will absorb the long wavelength radiation, right? Wavelength
Mhm.
infrared, and re-emit it at the same wavelength. So that's the idea. There's actually a there's a shorter way to say it, but this is the simpler way with with the more simple terms. Okay? And the thing is, what happens here on the other side with the greenhouse gases? What happened there? What happens to the what happens to the short wavelength infrared? The greenhouse gases are actually transparent to them. Okay? Let's put it here. The greenhouse gases are transparent to the short wavelength infrared. So what happens? They just pass through. Okay, and this effect, this wavelength here, is what causes the Earth to get warmer than -17 degrees Celsius. So without greenhouse gases, we would freeze. Life wouldn't exist. Okay,
Mhm.
but the problem now is because we are putting more greenhouse gases, we're making it less transparent. Sorry, not less transparent. We're putting more and more greenhouse gases. We're making more reflectors, so to speak, right?
Mhm.
So what do we write here? So for the enhanced greenhouse effect, so let's use black for this. So enhanced greenhouse effect um, traps more heat. So that's why we're getting warmer and warmer and warmer. Okay. All right. The last thing I want to cover, this is not really covered much in the exams, but I just want to cover this. How does it work? Okay. Now, how does the greenhouse effect actually happen? Okay. Now, to do this, I want to compare this to microwaves. Okay. Now, microwaves versus infrared. Now, in microwaves, do you I'm just curious. Do you know how microwave ovens actually work? Like, how do they heat up the food in a physical
Um,
sense?
so I learned
Mm-hmm.
that if you, I thought if you put something dry, it won't heat up
Yes, that's correct. It won't heat up as well.
as well. Yeah, but
Mm-hmm.
it'll still be hot. But like it goes in lines. So like there,
Mm-hmm.
if you put chocolate in, and if it doesn't spin,
Right.
like you can see lines
Yes.
that where the chocolate melts.
Yes. All right. Now, the reason why that is because microwaves have a particular wavelength. In this case, this is approximately 10 cm. Okay, 10 centimeters in wavelength.
Mhm.
Now, this 10 centimeter wavelength means it's got a certain frequency. I'll just call this name, call that frequency F res, like that, F res. Okay. Now, I say res because this is for resonance. Have you heard of this term, resonance?
Yes, but I don't know what it means.
Okay. So resonance is basically if you have two objects. Okay, let me get to the main board
And
first.
they're like in sync with each other or something.
Yeah, something like that. To be specific, um, guitar strings would be a very good example here. And I know you have a guitar,
Oh,
right?
yeah.
One way to tune a guitar, if you don't have a tuner, one way to tune it is like you like put one string, play a note on a certain string, and then the string below it should sound sound the same, right? Same note.
Yeah.
Now,
Unless they're both out of tune.
but if you're looking at and you're tuning your guitar and then you play one of the strings, the other one will vibrate without you touching it. That's
If
resonance
it's the same note.
because it's the same note exactly. They're the same frequency. So the idea
Mm.
here is if we go back here, this microwave has the same frequency as the um, FRES is equal to the frequency of water molecules flipping back and forth. The frequency of water molecules flipping back and forth. Okay, so that's the idea for microwaves. In infrared, it's the exact same idea, but instead of using microwaves, you're using infrared. And instead of water molecules, you have the the greenhouse gases. So in this case, this infrared, so this is gonna be infrared. This is the long wavelength infrared, right? Um, the frequency of which is also equal to the frequency of the CO2 and whatever other greenhouse gas molecules flipping back and forth. Okay, so that's the idea there. The carbon dioxide and the other greenhouse gases have the exact same resonant frequency as the infrared they're absorbing. That's why once they absorb the infrared, they emit it back at the same wavelength. Okay, so this is the last bit of it. So, all right, now that we know the greenhouse effect, I'm gonna go get a. Okay. Okay, I did not understand that guy. Somebody wrote some. Okay,
Yeah, it's nothing.
it's nothing, I think. All right. So anyway, let's not mind that. All right. So anyway, going back to what we were saying. So the greenhouse effect is important, right? Now, what I'll do here is I'm just gonna try to look for a problem about the greenhouse effect. Oh, I gotta check something out real quick. Hold on. Where's the desktop? Okay, here we go. Okay, I'll just use a book problem here. I'll just post it here for us to work on. Went too far. Okay, hold on. The book's loading. It's got too many pages. Hold on. Okay, I'll just go block that user now because it's just spamming
No,
messages.
no.
Well, okay, at the moment I won't yet because he's still a bit fun, but moment I see something, I'm blocking. All right. So anyway,
Okay.
that's 9. Okay, a little bit more. Okay, give me a moment. I'm just looking for a problem that would best fit what we just did here. Okay, then maybe on the next on the next meeting we'll go through the interpreting some graphs. Okay. Ah, it's not that, not that, not that. Okay, here. Let's do this one problem here. Mm-hmm. Okay, this one's interesting, I guess. Okay, at this point, you're not actually expected to calculate the actual amount of temperature increase that the greenhouse effect would have on a problem on a planet. So, yeah, we don't need to go into the math for the greenhouse effect. It's all concept for that. The only math we have so far is albedo and black body radiation. Okay. Later we will have more math with
Mm-hmm.
some. We'll have some more math later with graphs. Okay. So, in this case, we have a black body, temperature T1, emitting radiation towards a gray body of lower temperature T2. I'll just help you out and label which one is which. This is the black body. This is the gray body. Now, gray body means black body, but emissivity is not 1. Okay. No radiation is transmitted through the gray body. So, what does that mean? It simply means it's all absorbed. Well, it's all either absorbed or reflected. Okay. All right. So, all right. So I'll do the first part to help you out how to do it, and then you do the others for A. Okay. So, all right. So using all the symbols, state for the intensity radiated by the black body. Remember that the power. Let's just put the formula in. Power equals emissivity sigma area T to the 4. Right. So this is the same as saying the intensity is equal to E sigma T to the 4. The area disappears because you divide both sides by the area. Okay. All right. So with this, how will you do the first one? The first one, the intensity radiated by the black body would be this one. A part 1 would be equal to intensity is equal to emissivity is 1 for a black body. Then we just say sigma, and then the temperature of the black body is T1. So I'll just T1 raised to 4. Okay. So how about part 2? What's the answer?
Mm. Part one.
Mm-hmm. So it's radiated by the black body.
So so like the line is pointing to the green
Mm-hmm.
or
The gray
G,
one. Yeah.
the gray one. Yeah. And radiated by the gray is the vertical line from
Mm-hmm.
gray to B.
Mm-hmm. That's correct. So what would the
Um,
intensity of the so which one are we referring to for part 2? So this is part 1, right? Which one is part
Mhm.
2? Is this or that?
um, Part two is the one you said that.
Okay, the third one. This one. This
Yeah.
is part 2, correct.
Mhm. And absorbed by the gray body is the
Mm-hmm.
one that goes through.
Okay, so this is part 3, right? And therefore this is part 4.
Yeah.
Okay, great. All right, so part 2, what would the formula be for the radiation for the intensity of the radiation
Oh,
radiated by the gray body? I
I equals
equals
P over A. Wait, I'll go look at it. P over A, yeah. Power over area.
Yes, that's true, but we're not really given anything else here. We're not given the power.
Mm-hmm.
Okay? Since we're not given the power, we have to use the terms T1, T2, emissivity E, and sigma. No other symbols. Again, your clue is right here. The intensity is going to be given by this, right? Okay. I think okay, I need you to read this bit again. So again, the gray body, the temperature is T2 and the emissivity is E.
E.
Okay.
So it's one.
But it's not 1 because it's a gray body.
Oh, black body is 1.
Yes,
But gray
black
body is
body is
not 1.
automatic 1.
Okay. Hmm. Isn't this the equation? Yeah.
Exactly. That's already the equation right there.
Yeah.
So what do you have to write? Which one though? Which temperature are we going to use? T1 or T2?
T T2, right?
T2, correct. So E sigma T2 raised to 4. Okay. How about part 3?
Part 3. The equation for part 3.
Mhm.
If it's absorbed by gray body, then is it the albedo? No. Emissivity.
It is supposed to be the albedo. Now, one big thing here is the albedo normally means it's just the amount reflected, right?
Yeah, and if it's 0,
If nothing is reflected, either everything is absorbed or part of it is absorbed and part of it is transmitted.
right?
But it says here nothing is transmitted, so it's all absorbed. So the only possibilities are either reflect or absorb. So so for part 3, how much does it absorb and how much does it reflect?
Part 3, how much? I think it absorbs. Uh,
Mm-hmm.
it absorbs. Oh, like I think it kind of refracts it as well.
It may be doing that, but for this particular unit, we don't need to think about refraction anymore, or we just think reflection or absorption.
Yeah.
Okay.
If I think it's absorbing like 50, like half of it, because like I can see the other arrow is the same length, the one being
Okay.
reflected.
Oh, okay. That's a very good point. That would be true if we were dealing with vectors. Okay, but in this case, we're not really
Oh,
dealing with vectors. But yeah, could be. That's possible. Okay, I'll just tell you the answer to part 3. The intensity of the radiation absorbed by the gray body, okay, would be equal to the intensity here would be equal to still E, still sigma, and still T to the 4, but that's going to be T1.
T1 is.
Yeah. Why?
Oh, okay.
Okay. Have you figured out why it's T1?
Because it's the temperature emitting radiation,
This is because this is the
like
mhm.
emitting radiation.
Yeah, that's correct. So
Sorry,
yeah, go ahead. Just say it first before we continue.
is it I? Is it because it's the temperature of the black body emitting radiation to the green, like to the gray body? I mean,
Mm-hmm. Right. It is.
like that's the temperature that's being received
Mm-hmm. That
by the
is.
gray body.
It is. It's the temperature received by the gray body. Exactly. So that's why
Yo.
let's just label that here. So received and absorbed to be more specific, right?
Mhm.
And absorbed. Okay. And how about part 4? Let's put part 4 here because I don't have enough space there. Part 4 would be what?
Reflected by the gray. If it's reflected by the gray body,
Mm-hmm.
it's T2, right?
Mm-hmm.
Um, I equals E.
Right.
Stefan Boltzmann T42, no? Or
T.
can you put 1 for E?
Okay.
Because
No,
it's going to the black body?
no, it's not. But remember, we're looking at the one reflected by the gray body. So you
Oh.
want to see how much is reflected, right?
Mhm.
Okay. Um. Okay. I'll tell you the answer here. This is gonna be 1 - times sigma T1 to the 4. Okay, again.
Huh.
Okay, 1 minus E. Okay. Why? Because remember, the gray body has already absorbed that has absorbed this. So the rest is reflected. So
Mhm.
so let's think about it this way. So this is the incident on the gray body. So this is the gray body. And then how much of it is absorbed? Let's just say in percentage. This is 100%, right? That's where the 1 comes from. Okay. Now it absorbs how much was it again? It absorbs E sigma T1 to the 4. So how much should be left over and reflected? So left over is equal to 1 minus E sigma T1 to the 4. So that's how much is reflected.
Hmm.
Okay. All right. So
It's 1 minus E because you're trying to find the albedo
mhm,
of the gray body.
yeah. So that's the gray body there, right? So this is part of it. And then the second part of it is this is the black body right here, right? How much did it
Yeah.
and how much is it actually emitting? How much is that 100%? That's going to be the intensity here would be equal to sigma T. Sorry, this is T2, right? Sorry, that is T1. So this is going to be T1 to the 4. So what am I
Mhm.
going to do here? That's going to be sigma T1 to the 4 minus E sigma T1 to the 4. I factor out sigma T1 to the 4. We're left with 1 minus E on the inside. Sigma T1 to the 4. Okay, so that's why the
Wait, so
answer
what
is
does
this.
1 minus E represent?
This 1 minus E basically represents this minus this.
Yeah. Okay.
All right. Uh, okay. I think, yeah, so I think for the next lesson, we can go back to this. I'll get more concrete examples later. Okay. And then again, like I said earlier, we will actually not need any math for the greenhouse effect bit. It's really just explaining what it does.
Right.
All right. And then afterwards, that's on Sunday, we'll go to some graphs. Okay. Now, before we end, CJ, I just want to let you know, this Sunday is gonna be our last lesson for a while. Okay, because I'll be busy the next 2 weeks.
Okay.
Okay, I think I'll be back by Thursday, the week after next.
Yeah.
Okay.
Plus, I have mocks week
Oh, you have
when you're
mocks.
gone.
Oh, perfect then. So perfect. You need the time. Well, okay. Here's
Yeah.
the deal, though. I won't be able to do live lessons like this, but if you have questions, just send me whatever. I'll try to answer if you need anything. Okay.
Sure.
All right.
Also, I was wondering, like,
Mm-hmm.
does your school upload their average IB score?
I don't know. I think we do. No, we don't. We don't upload the score. We do know our score, our average score, but we don't publicize it. I think.
Oh, okay.
All I'm gonna say though is we're consistently above average.
That's good. I don't know. I was wondering what the average was.
Mm-hmm. Yeah,
What was the average?
I think mostly for the world the average is a little bit above 4. So let's say 4.2 or 4.3 for the world average.
Wait, so that's like 28.
Mm-hmm.
IB 28 score.
Yeah.
Okay.
Again, that's world average, but for yeah, for our school, I hope for your school it's the same thing that you're a little bit above average is already good. Okay.
Mm-hmm. That's good.
All right, great. So, okay, so I guess we can end here today, CJ. So next week, next lesson, little bit more of this, and then the graphs. Okay. Right. So any other questions before we go?
That's it.
We're all good.
Thank you.
All right. So I'll see you next time then, CJ. Have a good evening.
See you. Have a good evening. Thank you.
Bye bye now. Okay, so that's done. We're done with the lesson. So for those who joined, yeah, okay, we're good. We're good. Don't worry about it. As long as you behave yourselves, you're fine. I still consider that behaving yourself, so we're good. What do I consider not behaving? Spamming and, crude language will automatically get a ban, okay? Just so we're clear. So anyway, so that's it. So hopefully, if you did stay and listen to that, I hope you learned something. Basically, just to summarize, greenhouse effect, really important. Even though it's got a bad reputation right now, it's actually important. We just need to control it. We just have to make sure it doesn't, run away from our control. Okay. I didn't mention this earlier in the stream, but I want to say this now. One of the things that you may have heard that, what was that? That Venus is way hotter. Yeah, Venus is way hotter than Mercury. Even though Mercury is the closest planet to the sun, Venus is way hotter. The main reason for that is the atmosphere of Venus is actually all, okay, is actually all just carbon dioxide. It's 90% carbon dioxide. Okay, so with that, I will go ahead. Before we end though, don't forget to, let's just do this. Okay, don't forget to follow us on the social media accounts. Don't forget to like, subscribe, and hit the notifications there. Now, again, announcements are done on TikTok, Instagram, and Facebook, and the live streams are done on Facebook, YouTube, and Twitch. So, right. All right, so with that, we'll end the stream. Thank you for coming, and again, have a good evening, have a good day, morning, afternoon, wherever you are in the world, and let's stay freaky, everyone. Bye bye now.